chapter 11 is all about the atmosphere. So right off the bat, we need to talk about what the atmosphere is made out of, and we like to call this composition. So first of all, to kind of put it in perspective, our atmosphere is technically gases, right? Okay, 90% of our gases lie within the first 10 miles of the atmosphere. 95 or 99% of the gases lie within the first 19 miles. And so to kind of put this into perspective for you, if I was to draw a circle on the board that was, I think it's 40 centimeters, so that's like a meter stick. If I were to draw a circle on the board with the meter stick as the diameter, if I drew a little tiny circle in the center, the thickness of a pencil lead, that is what 19 miles is. So the majority of our gases are very, very, very close to the surface. However, you can't really measure where they stop, because it's not that they ever really stop, it's just that they become thinner and thinner and thinner and thinner. Okay. So to kind of, our atmosphere is broken up into several different types. We have our exosphere, that's the farthest, that's space. Okay, then we go into our thermosphere, then we go into our mesosphere, but the ones we're actually concerned with are the stratosphere, that's where the ozone layer lives, and then the troposphere, that's where we live. The only things that really go into the stratosphere are some airplanes, but everything else takes place. I think Britain had the Concorde, although they've been taken out of commission. The Concorde would fly into the stratosphere, but most of them fly in the troposphere. Okay, so, the troposphere is the region I was talking about where the majority of human activities take place. This is commercial airliners fly at about 30 to 35,000 feet. That's right at the border of the troposphere and the stratosphere. So just kind of a breakdown of our atmosphere. 78% of our atmosphere is nitrogen. 21% is oxygen. 0.934 is argon. 0.0321 is carbon dioxide. And 0.0039% is a mixture of all of the rest of these gases. So if you think about how much oxygen it requires for just the human race to breathe every single day, well, that's only 21%. So it kind of puts in perspective, not only that, but think about how much CO2 we exhale every single day, and that's only 0.03%. So it kind of gives you an idea of how big the atmosphere actually is. Okay, one part down at the very bottom, which actually affects a lot of our processes we're going to talk about today, is water vapor. Water is one of the only gases that the percentage can vary. So it can vary from anywhere from 0 to 4%, depending on the season, depending on the humidity levels, depending on what region of the world we're talking about. And so this number, this is called relative humidity, and this can change a lot. 0 to 4% is a very big fluctuation versus the other percentages that don't really fluctuate very much. All right. So, what is the purpose of our atmosphere? Well, there are lots of purposes. We're going to talk about a few of them. So the first one is photosynthesis. Okay, photosynthesis is where plants absorb carbon dioxide and they mix it with water and sunlight to form oxygen and sugar. The sugar is then eaten by other things to produce energy for them, because not everything can produce the energy for itself. Plants also consume their sugar, and they actually do it in the reverse at nighttime. When there is no sun, plants don't die throughout the night, right? What they do is they do the opposite. They consume the sugar they just made to keep themselves going throughout the night. The next one that we talk about is greenhouse effect, and we're going to be talking about this a lot. Greenhouse effect is a good thing, and it's a bad thing. Okay, you guys have all heard about global warming, right? Well, global warming and greenhouse effects kind of go hand in hand, but they're two different things at the same time. The greenhouse effect is what prevents large-scale heat loss. And so it's kind of like a blanket. Our atmosphere kind of traps in the heat. It doesn't allow the heat to escape, which is good, because if we compare this to the moon doesn't have an atmosphere, and it's really, really, really cold, and there's no plant life. There's no nothing on the moon, correct? Well, the moon doesn't have an atmosphere. Well, in relation, we're about the same distance from the sun as the moon. So if we didn't have our atmosphere, we would be as cold as it is on the moon. And so again, we wouldn't have the plant life that we have now. We wouldn't have the animal life we have now. Okay, the two gases that are responsible for this blanketing of heat are our carbon dioxide and our H2O vapor. And so like I said, we need carbon dioxide because we need the greenhouse effect. If we didn't have carbon dioxide, we wouldn't be able to blanket our atmosphere. We wouldn't be able to trap the heat. there's a very fine line between we want to trap the heat, but we don't want to trap too much heat. Okay, so we're going to talk about that a lot today. All right, so let's talk about the carbon cycle. The carbon cycle is very, very, very important, and it's honestly what keeps our planet going. So first of all, like I said, CO2 is very important. It's what blankets the atmosphere. It is honestly one of the things that allows us to maintain life on the planet. But we breathe out carbon dioxide, plants breathe it in. So we have to have some sort of cycle in order to keep it going round and round and round. So first of all, CO2 is converted by photosynthesis. Okay, it's converted back into oxygen, it's converted into sugars, so on and so forth. This is what we call fixing carbon. Because when carbon dioxide is in the carbon dioxide form, we as animals, and not only us, but animals in general, cannot use it. And so it's useless because we can't use it in the current form. CO2 we can't really do anything with it. And so we call this process fixing it. Because in the carbon can be eaten by animals, it can die or decay. Plants can die and decay on the surface of the ground or the ocean, so on and so forth. And in the process, they're putting carbon back into the atmosphere. Or if we let that decaying plant life sit long enough, it'll just become under pressure and more pressure and more pressure and more pressure, and then it turns into a fossil fuel. So this would be like coal or oil or petroleum or methane gas, so on and so forth. But it has to sit. That process is a really, really, really long time. Once carbon is in an animal, so once it is consumed, we can then convert it back into CO2 by doing respiration. We breathe out CO2. We can, again, animals can die and decay and put it back into the earth that way. But honestly, the majority of what animals do is when they decay, it doesn't happen near as quickly as plants do, so they are most likely turned into the fossil fuels. Again, over thousands and thousands of years does that process take. Okay, so this is the carbon cycle, and up until the 1700s, it was a nice, pretty cycle. Nothing was really disturbing it. Well, us as humans, have done things to increase the amount of CO2, and this is disturbing the carbon cycle because it used to be a teeter-totter that was level, and now it's starting to teeter-totter onto the verge of more carbon dioxide and less everything else. And so now it's starting to outweigh its counterparts, and so it's no longer working in a nice, pretty cycle. So there are several things causing this. The biggest one is forest destruction. Basically, we cut down a tree, and what do we usually do with trees? We burn them in one way, shape, or form. We make paper, but in landfills they get burned, right? We cut down trees for firewood. For the most part, deforestation, the majority of it is burned. Well, in the burning process, you're releasing carbon dioxide. So you're putting all that carbon dioxide into the air, and then not only that, but the tree can no longer absorb carbon dioxide and turn it into oxygen and sugar. So you're putting carbon dioxide in the air, and you're taking away the ability to fix it. So it's kind of like hitting it twice in the negative direction. This honestly takes place in the tropics, so around the equator. And in 1945, we had about 14% rainforests, and since then, in the last 60, 70 years, it has dropped down to 7%. So if you think about that's a very short amount of time considering the length of time that we've been measuring this. Another thing that increases the CO2 is the high demand for fossil fuels. Back in the 1700s, we didn't have electricity. We didn't have cars. We didn't have all of these things that we need to burn fossil fuels for. The only thing they needed to burn fuel for was for heat for their houses. And so yes, they did it, but in such a small percentage to what we do now. So these things lead to climate change. Okay, so the first one that we're going to talk about is global warming, and I'm not going to tell you that global warming is happening or it's not happening because honestly there's not enough evidence in either way, shape, or form. But we're going to talk about the thoughts out there about global warming. So first of all, our atmosphere lets light through, but at the same time, it does not lose the heat. We just talked about it. We need the greenhouse effect because the greenhouse effect is what blankets our atmosphere to keep it warm enough for life. So these greenhouse gases that we are worried about is water vapor, but we don't really, we as humans can't affect water vapor. Water vapor is evaporation and heating up based on the season, based on the climate, based on there's nothing that we really do to affect the amount of water because the amount of water on the earth is so great. I mean, think about how much ocean we have. there's nothing we're going to really do that's going to significantly change the percentage of water. But what we significantly change is the percentage of carbon dioxide. And not only do we change the amount of carbon dioxide, but we also are starting to produce more methane gas. Now, methane is CH4, and it is often produced by anaerobic decay. And anaerobic decay is what happens when there's no oxygen present. So this happens at the bottom of the ocean. There's no oxygen at the bottom of the ocean because it's underwater, right? This is what happens in extreme climates, like at volcano vents, okay, when there's a lot of other gases pushing the oxygen away. So anaerobic processes, they don't do photosynthesis. They're going to break it down, but they're not going to release oxygen. They're going to release methane. And methane is a type of greenhouse gas. Some other examples of things that create methane are cows actually produce a lot of methane. Examples off the top of my head are really bad. Oh, methane is also, when we're talking about fossil fuels, when we're collecting coal, when we're collecting oil off the ground, often there's also methane in these reserves. That's why there's oftentimes a lot of explosions in coal mines, because if they tap into the methane reserve and then they have a spark, which when you're hitting things and drilling, you're going to have sparks, it creates an explosion. So that's usually fossil fuels and methane go hand in hand. So what is the evidence for global warming? Well, first of all, we have to determine, are the CO2 levels actually rising? Okay, well, CO2 levels have been monitored at the top of Mauna Loa, which is a volcano, since 1958. This is in Hawaii. This is when we actually started noticing that there might be a problem, so we started trying to keep track of it. And what they noticed was that in 1958, there was 316 parts per million. So when they measured the air, we have 316 carbon dioxide molecules per million of everything else. Okay? Now, so, I don't know, 50, 60 years later, there's 400 parts per million. So that doesn't look like a pretty significant rise, but it's rising at a rate of 2 parts per million a year, which is a pretty significant rise when we're considering that it only took us 50 years to make a big, big difference. But looking at 50, 60 years of data in the grand scheme of the Earth is not really very much data, right? So because we need something to compare. Is 316 parts per million a good amount, a bad amount? Is that high? Is that low? We need something to compare it to. So basically, we can find other sources. We can use other ways to measure the CO2. So what we can do is we can find air samples trapped. So like, we've been bottling things for a really long time. People have canned things for a really long time. Little things like just buttons. When you make a button, they like slam them together really fast, and sometimes there's pockets of air that get trapped in the button. So, I mean, if we can find an air sample that's been undisturbed in something, and we can figure out what year that item was made or produced or whatever, we can then calculate the carbon dioxide in that sample of air, and we can put a date to it. So it's kind of a roundabout way, but since we really didn't start monitoring it until 1958, we kind of had to get a little bit creative to really see what's happening with carbon dioxide. In what we noticed while we're measuring these other items is that our carbon dioxide levels were approximately 280 parts per million consistently until the 1700s. What happened in the 1700s? Industrial Revolution. So that's when we started assembly lines and making products and housing electricity, and that's what started it all, was in the 1700s. So up until then, it was pretty consistent at 280. So from 1700 until now, we've almost doubled it. Well, not quite doubled it, but I don't know, 50% increase or so. Another way we can do this is to look at ice samples. Okay, ice samples are like in the Arctic or in Antarctica. What happens is every year it snows. Well, in Antarctica and the Arctic Circle, it never really melts. And so what happens is it snows, and then it just gets packed down, forms ice. And the next year it snows, packs down, form ice. And this happens year after year after year because it never technically melts and goes away. And so we can, when it melts and it's packed down, it traps air pockets. And so we can analyze these air pockets again. And just like tree rings, we can tell how old the ice sample is by how many layers of ice we see. So we can tell how old the air samples are based on where they are in the ice layers. Based on the temperatures for the planet, ocean levels rise and fall too. And this has happened throughout time. We know that we go through ice ages, we go through extreme temperatures, so we always have this fluctuation. High temperatures usually mean low oceans, which means our H2O18, because water, there's two isotopes for oxygen. We have oxygen that's 18, we have oxygen that's 16. Well, theoretically, the 16 should evaporate first because it's lighter. So theoretically, when our ocean levels are down low, which in high temperatures means it's evaporating, our oxygen 18 should be left behind. So then we can kind of measure this because we can see how much oxygen 18 was in these samples. If there's more oxygen 18, it lets us assume that the ocean levels were lower. And so then we can coordinate that, oh, the temperatures were higher. Okay, so vice versa. If it was low temperatures, then that means there's not as much evaporation. So there should be less oxygen 18 present in the water. So then we can, again, assume. Now, was anyone around back then that made recording, so on and so forth? No. So a lot of this is just assumption, but they're good assumptions. So let's go back to, is our carbon dioxide rising? Well, carbon dioxide and CH4 levels have gone up and down in the past. That's a known fact. Okay, we have ice ages, we have ages of heat. They do go up and down. So we have to try to determine, is it higher than normal? Yes, we're rising, but is it rising more than it should be? Because we do have normal periods of fluctuation. So, to put it in perspective, the 400 parts per million levels that I was just talking about are higher than they have been in the last 800,000 years. So right now, our carbon dioxide is higher than we've seen in almost a million years. So we're kind of in uncharted territory right now. We're really not sure what's going to happen. In the last 800,000 years, it has never exceeded 300 parts per million. And methane, which as I told you, didn't used to be of concern, used to be around 1.7 parts per million. Well, now it is 2.5 times higher than that. So we're seeing a significant increase in methane. And the reason we're seeing a significant increase in methane is because we're seeing more farmland, which equals more livestock and less trees, less everything else, because our population is increasing exponentially. So we need more food to feed everybody, which means more livestock, more farmland, less trees, deforestation. So all of these things kind of go hand in hand. So, again, more evidence for global warming. Planet temperatures have risen 7 degrees Fahrenheit in the last 20 years. The Arctic ice pack has decreased 7.5 million square kilometers in 1958 to 5.5 million. So we've lost 2 million square kilometers of ice in the Arctic, which that's a lot to me. But what do you think that's affecting? Because we don't live in the Arctic, so how is that going to affect us? What happens to that water? It makes the ocean rise. And what happens as the ocean rises? The coastal cities are going to start being flooded, and usually the coastal cities are at or sometimes even below sea level, and so eventually some of these cities that are right on the coast are going to be flooded and they're not going to be able to be lived in anymore. The thickness of the ice, so not only has the ice started to melt, but the thickness, it's getting thinner, which means the sheets of ice up top that I said usually they don't melt, they just layer and then layer and then layer. Well, now they're starting to melt. They're no longer forming these ice layers. They're starting to melt. And so that, again, but what happens when water melts and it starts to run off? Doesn't it cause further melting? Like if you set an ice cube on the table, yeah, it's going to melt. But if you set an ice cube in water, doesn't it melt faster? Okay? Water, as ice melts and forms water, it causes the other ice to melt even faster. Okay, this leads to glaciers melting, and over the last 20 years, our winter has actually decreased by 18 days, which again, doesn't sound like a lot, but in the grand scheme of things, 18 days out of 365 that's a 5% decrease, so that's pretty significant.
Is that saying when weather decreased, or when we actually...
Just the time frame from like the beginning to the end, when we notice a significant decrease in temperatures and when it starts to increase. And this is the world as a whole, not just us here. Because our weather is crazy here, so who knows what's going on. Concerns of warming. So why does it matter if we do global warming? Well, first of all, short-term effects, we have unpredictable weather changes. We live in the Ozarks. We're familiar with those. What's going to happen is also the equator is going to start getting warmer and warmer and warmer. And so the places where they grow crops are going to start navigating towards the north because you can't grow crops really, really hot, but you can't grow crops really, really cold. So the areas that grow crops are going to start migrating towards the poles. And then the equator is going to lose the ability to support these crops or farm because if it's too hot, livestock isn't going to be able to survive. In the spring and fall, when we have violent weather like tornadoes versus hurricanes, we're going to have a greater, because the higher the temperature is, the more violent the hurricanes are. So the more around here, it's when we have our drastic weather changes that causes tornadoes, right? So this could cause more violent weather. It could also decrease the amount of biodiversity, so a lot of species could go extinct because, again, if their habitat goes, they're going to die. And then this could also increase the spread of disease just because people are going to be forced to migrate to places they wouldn't normally go. So long-term concerns of warming. It, again, could cause rising ocean levels. And the most important thing is melting of the permafrost. Now, permafrost is technically ground that is permanently frozen, and it's been permanently frozen for thousands and thousands of years. And this is 20% of the land. Well, it doesn't sound like a big deal for the land to start to thaw out, but in the process, when it starts to thaw out, all of that material that's frozen is going to start to decay. Because frozen stuff doesn't decay, but as it starts to thaw out, all of those plant life, whatever that had died and is now frozen, is going to start to decay. Well, decay will produce carbon dioxide. So if all of this 20% of our land starts to thaw out, we're going to have a great rise in decay, and it's going to create more CO2. And it's just going to tip our scales even further in the wrong direction. This could possibly, in the end, outweigh us in our contribution to the carbon dioxide problem. If this happens, once this starts to happen, we can't go back. So we need to figure out a way to fix this before this starts happening. Because once it starts happening, we can't stop it. That is 100% out of our control. Okay, so what are our major sources of carbon dioxide? Well, first of all, coal power plants. We talked about that a lot last unit, didn't we? Okay, we have 600 in the United States. They burn 1 billion tons of coal per year, which means they are going to generate 2 billion tons of carbon dioxide per year. Okay, if we were to convert this to natural gas, it would cut the CO2 in half, which is a start. But if we were to convert this to nuclear, solar, or wind power, or maybe a mixture of all of the above, it would nearly eliminate the carbon dioxide. So last unit, we kept talking about nuclear power, and we learned about the benefits, but we also learned about the drawbacks, right? But when we look at how bad coal power plants are and how they really are causing issues, it's kind of a push to maybe we need to figure out how to make this nuclear power more efficient. We need to figure out ways to make it safer because we're starting to run out of options. We need to figure this out before it gets to the point of no return. So if we look at how much coal is burned per country, China burns 7 billion tons per year. The U.S. is 5.3, European 3.6, India is 1.6, Russia is 1.5, and Japan is 1.1. So if we look at this, it looks like China makes a whole lot more than we have, right? But if you look at it in comparison to how much their population is, they are double, triple, quadruple our population. So if you divide it up per person, we are outweigh anyone else. We produce more carbon dioxide waste than any other country per person. All right, so now let's switch gears a little bit and let's start talking about the ozone layer. Okay, so ozone production. Ozone is a special kind of oxygen. It is O3. Oxygen usually exists as O2, but in the ozone layer, it exists as O3. And this occurs in the stratosphere. And what happens is ultraviolet light comes and it strikes an O2 molecule. and then it kind of breaks it in half for a short time, and it kind of energizes it, and it goes over and it slams into another oxygen molecule, and then for a short second it becomes O3. Okay, and then a light strikes it and it causes it to break apart into O2 and an oxygen molecule, and then that oxygen molecule goes and flies and hits another oxygen and it slams it together, and so it forms O3. And this process just happens over and over and over and over and over and over and over again. And it's very, very important, because if all of the sun rays hit our surface, that would be bad. That is way more radiation than life can handle. If it wasn't for the ozone layer, we would see an increase in skin cancers. We would see an increase in the amount of how hot the surface was. We wouldn't be able to grow our crops the right way. The ozone layer deflects a lot of that radiation back because we don't need it all. If we had it all, it would be bad. Okay? Again, think about the moon. It has no atmosphere. Is there any really life on the moon? No. Why? Because we have all of these things. So if you want to, there's a little video that you can watch on the PowerPoint. You can click on it in your own time if you really want to watch it, and it kind of explains how ozone is created and what happens. But UV light creates it, and then it destroys it, and then it creates it, and then it destroys it, creates it, destroys it. It's like a vicious cycle. But nothing's up there in the ozone layer, so this cycle can continue without effect because there's nothing up there to cause it to stop. So what's happening to the ozone layer then? If nothing's up there, what's going on? Well, pollution is up there now. Okay, back in the 1950s, I want to say, maybe 1970s, we started really coming up with some chemicals. So nitrogen oxides is the first one we're going to talk about. These are used in aircraft. They're also produced in nuclear explosions, and they're also used in CFCs. Does everybody know what CFCs are? Chlorofluorocarbons. They are used in Freon. They are used in propellants. They are used in a lot of aerosols, or they used to be. Now they're not used in aerosols because they're so bad. But we didn't know that at first. Usually when we come up with a new scientific breakthrough, we know the benefits way before we know the drawbacks. Okay, so basically what happens is our nitrogen oxide floats up into the atmosphere, solidifies our ozone layer. Well, in the ozone layer, our UV light is breaking apart this ozone really fast. It's breaking up into O2 and O. And oxygen is a very special molecule. He doesn't like to be all by himself. So he will do whatever it takes to bond with somebody else. And so if all he has to bond with is an O2 molecule, he's going to slam together and they're going to form O3. But that's a process that doesn't really like to happen. It's a hard process to happen. So what's going to happen is as we go up here, it's a lot easier for that extra oxygen to bond to NO than it is to bond to O3. And so what's going to happen is as our UV light breaks off that extra oxygen, it then goes and forms to NO. And so it's no longer part of the cycle. Once it's part of NO, it doesn't break apart. And now we have O2 over here by itself. But O2 is not O3, and it's not going to do that chain cycle of breaking off on the UV. So it's no longer protecting us. And so as we go up there, as more and more nitrogen oxides go up there, and they're stealing all of these free oxygen molecules, there's no longer oxygen molecules to do this chain reaction to form ozone. So that's what's actually happening to our ozone layer. It's not disappearing. It's just no longer doing this. Yes. There's no longer doing this reaction because there no longer is any oxygen up there. It's all O2 and no longer is it O3. So yes, it's still there, but it's no longer doing the thing where it's protecting us from UV rays. Okay. Another thing down here that you can see, we have this crazy compound. Well, when it is exposed to UV light, which is the whole point of the ozone layer, this chlorine breaks off. Well, chlorine is very, very, very strong. You're talking about electronegativity, and he likes to bond with other people, and he will do so very well. And so he does the exact same thing. Whenever there is a free oxygen floating around, when it breaks off of the ozone, it sticks to the chlorine, and once it's stuck to the chlorine, it stays there for life. It doesn't go back into the O3. And so basically, all of these waste or pollution or whatever, once it floats up to the ozone layer, it steals those free oxygens, and once they're stolen, there's really no going back, and they can no longer form that O3 chain reaction. So we didn't really discover this until 1985, and if you remember, I said that those things started becoming produced, I want to say in the late 60s, early 70s is when stuff like that started happening. Well, we didn't really discover this until 1985, and we discovered this by accident when a scientist was doing some studies in Antarctica. What he noticed is that the hole would grow and shrink each season, but what he noticed is that each season it got bigger. So why would a hole get bigger every single season? There must be something happening to cause this chemical reaction to be increasing or the ozone to be decreasing. Something must be happening. And so what they did is they studied the ozone layer, and what they found is that there was some chlorine up there, which doesn't make a lot of sense. Why should there be chlorine in the ozone layer? That doesn't make any sense. It's not supposed to be there. And so then they were kind of able to backtrack it to the CFCs I was just talking about. Those became really, really popular in that time frame. And so we were able to track it back to that. So in the 1990 to 2000, we were supposed to reduce the CFC use by 50%. And we've actually done a pretty good job of cutting these out wherever possible. And when we can't cut them out and we have to use them, we try to contain them as best as possible so that the chlorine is not released into the atmosphere. In 1989, they actually found a small hole in the Arctic, and so that got us even more worried, and so this actually sped up the process of eliminating the CFCs. And in 1990, there was a complete phase out of CFCs and our other chlorine molecules, and 59 nations agreed to this, and so for the most part, this process has been completely phased out. Now, some old air conditioning units or some older cars will have some, but we're not perfect. And so eventually it'll be all phased out. And so what they've noticed is that this issue of the ozone is actually it's not getting better, but it's not exactly getting worse. So we found a way to kind of stop the destruction. Right, and your homework is on page 204, number 1 through 11. Again, I highly recommend you go back and at the very least skim this chapter because like I said, I have no voice, so I made this short and sweet, okay? Have a good night.